Okay, so we're going to go ahead and evaluate the determinant of this matrix. It's a 2 by 2, so it's pretty easy. It's going to be A times D, which in this case is 3 times 6, minus B times C, which is going to be 5 times -1, which is going to be 18 plus 5, or 23. And that would be the determinant of that matrix. Okay. We can use the determinant to figure out what the inverse of a matrix is. And on a 2 by 2, the rule is that if the determinant is not 0, we take the inverse of the determinant, 1 over the determinant of A, and we move some stuff around in the matrix. So if the original matrix is A, B, C, D, we switch the position of A and D, and we leave B and C in the same place, but we negate them. We take the negative values of whatever is in position B and C. Okay, so it's 1 over the determinant of A times this modified version of the matrix A. And we could also write that because the determinant of A is AD minus BC, as we just did. So this is a fully written out formula for the inverse of a 2 by 2 matrix. All right, so I'm just going to write that. Well, let's go ahead and do this. We want to find whether it has an inverse. So first thing we're going to do, let's call this matrix A. We're going to find the determinant of matrix A, which is going to be -2 times -4 minus 2 times 5, which is 8 minus 10, or -2. So it's not 0, so we can go ahead and do an inverse. All right, so the inverse is going to be 1 over the determinant, which is -2, times, and now we need to go ahead and switch the positions of A and D. So this is going to be -4 and -2, and we need to negate B and C. So -2, -5. And if we multiply that out, A inverse is going to equal -1/2 times -4 is 2. -1/2 times -2 is 1. -2 times -5 is, I'm sorry, -1/2 times -5 is 5 halves. And -1/2 times -2 again is 1. That would be our inverse matrix. Okay. So in the last lesson, we talked about the fact that matrix addition, subtraction, multiplication, we could do all of that, but there really isn't a matrix division. And here's how we get around that. Let's say we have an equation. These are all matrices. Matrix A times matrix X equals matrix B. And we want to solve that for matrix X. Well, what we'd like to do is say, well, okay, X is equal to B divided by A, dividing both sides of this equation by A. However, we don't have the ability to do matrix division. Okay, but if you think about it, if I say, 5x equals 10, and normally you'd say, okay, go ahead and divide that by 5, and we'll get x equals 2, and that's correct. But we also could say, you know what, multiply both sides by the inverse of 5. Well, the inverse of 5 is 1/5. Now, doing that is obviously the same as dividing by 5. Okay, and if we do that, we wind up with the same thing. Those cancel, and we get x equals 2, and that works. So what we're really going to do is, instead of dividing with matrices, we're just going to be multiplying by the inverse. We know how to take the inverse now. So looking over here, we could see that to get x, instead of dividing both sides by a, what we've done is multiplied both sides by a. And if we write this all out, ax equals b, and we say, you know what, we're going to multiply both sides by a inverse. That's going to be a inverse times x equals a inverse times b. And keeping the same order, of course. Well, notice that a inverse times a is the identity matrix. All right, so this is just identity times x equals A inverse times B. And the identity matrix times any matrix is just the matrix itself. So really we could say that this whole thing is equal x equals A inverse times B. Okay, so we're going to use inverses instead of division. Okay, so now we move on to the great fun of the inverse of a larger matrix. And, I'm sorry, the determinant, and we'll ultimately get to the inverse. Now, with a 2 by 2, it was nice. Okay, we just took the two diagonals and multiplied each diagonal and subtracted, and we were done. Here, we've got a whole lot more of a mess. We've got to do 3 sets of diagonals. Okay, so I'm going to take this diagonal, and then notice that we've rewritten the first 2 columns of the matrix here. So we could do 3 diagonals this way. All right, so we wind up with A1, B2, C3, right? 1, 2, 3, there. Plus this times that, plus this times this times this, minus the green diagonals, and you're going to get your determinant. Well, isn't that a whole lot of fun? All right, so we could do that here, but I don't really feel like it, okay? Because the calculator can rescue you. All of what we've been doing with determinants of matrices as well as inverses of matrices can be done on the calculator, and I encourage you to do so. All right, so let's just go back to this, and we're not going to do this. I mean, we could manually work it out, taking all of the products, -1 times -4 times -1 plus 3 times 6 times 0 plus 5 times 2 times 1 minus, and take the other diagonals. Yuck. Okay, let's bring up the calculator. And I already have this matrix in here, I believe. Oops, if I turn this on, it'll help. Second matrix, and I believe I have it in as matrix C. There it is. Okay, so what I'm going to do is I'm going to go back to second matrix, and I'm going to do math operations, and guess what? There's the determinant. So we're going to just choose determinant of matrix C, second matrix, and I'm going to select C from my matrix list. And it does it for me. The determinant of that matrix is 18. Okay. I could also do an inverse, and that would be, if I could see it, second matrix, and I'm going to pick my matrix, and I'm going to use the inverse command, which is x to the -1, right on the matrix button there. Okay. Notice the terminology is correct. The inverse of that matrix, there it is. It's long, it's decimal, so it's kind of scrolling off the side of the calculator. Okay, but there it is, and you can get your numbers. Okay, so you could do, of any square matrix, you could do the determinant if it exists, and the inverse if it exists on the calculator.